Most of us have seen some similar C code like this, where it's just a for loop that increments a variable. The second line here looks a little odd, but it's just a simple bit shift. What it basically means that we have a 4-byte integer where we have a 1 in the least significant position, and we shift it 20 times to the left. And once that it's been shifted 20 times, we get some integer that's close to 1,000,000, a constant. Otherwise, it's just a simple for loop where j starts at 0 and is incremented 1,000,000 times, roughly, by 5. And it will result in approximately 5,000,000. Now, let's say I run this code on an Intel Core i5 that's running at base frequency 2.4 gigahertz. What do you think the wall clock time will be in that case? Is it 17 milliseconds, 3 milliseconds, 7.5 nanoseconds, or 0.2 seconds? I'll go over the result and how we get there, but if you want to figure it out yourself, pause the video. Looking at the code in C, we can sort of figure out what we think the assembly instructions will look like. I imagine it will load the constants into memory in the registers 0, 1, 2, 3. Then it will do some sort of comparison between if we have reached the end of the loop and then the actual workhorse of the loop, which just increments the variable. And then at the end returns once we're complete. In total, I would expect around 3 machine language instructions per iteration. So in total, maybe 3 million instructions for the whole lifetime of the program. In order to actually benchmark it, we have to add some loop counters, which are these RDSDC Intel intrinsics right here, which just record the cycle count. So we record the cycle count before the loop and after the loop, and then return the value of j. Now, actually running the binary corresponding to this C code, we can see that it uses a microscopic cycle count to what we expected. A few dozen or so cycles. To really get to the bottom of this, we have to look at the actual assembly generated by the Clang compiler. Now, most of it is just assembly generated boilerplate, which is the upper part here. And the actual meaningful work of the program happens on this line, where the result simply gets moved into the return address of the program. So the compiler has actually looked at the code and figured out the result on its own. Just like we did earlier on, we figured out that the result will be around 5 million. The compiler can actually do the same thing, where it can look at a piece of code and see what is a constant and what is not, and then simply substitute the result of the constant. In this case, it's the sum amounting to approximately 5 million. If I compile this with the default settings of the compiler, we'll get something that's closer to our original approximation of the cycle count, which is around 3 million or so instructions. The original binary was not compiled with the default settings, it was compiled with this compiler flag -01, which controls the optimization employed by the compiler. And with this, we get some that resembles the cycle count we had earlier, which is just a few dozen cycles in total. So why is it that the O1 flag makes the code run so much faster? Well, there's this specific flag that it enables, and it controls the flow-sensitive tree-level conditional constant propagation. Effectively, what that means is that wherever the program sees constants, it decides to replace the value with that result of that constant. So for example, this x would get replaced with just the sum of 2 and 5, which is 7. Similarly, our for loop is just essentially one big complicated constant declaration, and the compiler has no issue with replacing constant declarations like this. This is called loop unrolling. Now, returning to the original multiple choice question about the wall clock time, the actual correct answers were 17 milliseconds and 7.5 nanoseconds, each corresponding to no optimization and -01 optimization levels, which result in 4 million and 20 clock cycles respectively. The actual correct answer to the question would have maybe been it depends on the compilation flags. That's all for now. Thank you for your time.